Hello. So finally, this is the last set of exercises that you're going to watch. Um, there are three exercises here. The video is itself quite quick, mga 20 minutes lang. Okay, and afterwards you're also going to solve some problems which you hopefully will be able to submit by before the class time ends. Okay? But before 3 o'clock. Pero 6 p.m. pa rin yung deadline na ibibigay ko sa inyo. Okay, and so like I said, meron ng tatlong exercises dito on the frequency response of AC circuits. I highly encourage you to solve the exercises and just make, in this case, just one submission. Okay, so select one problem, make one submission, and then that's it. Okay, so this is the last meeting as well for the asynchronous mode. I'm going to see you on Tuesday, okay, para sa ating lab class, and on Wednesday para sa ating lecture class face-to-face, okay? Happy weekend, and I'll see you next week.
The first problem that we're going to solve are these two questions. First question is to determine the cutoff frequency for each circuit in each of the figures. And the second question asks us to determine the bandwidth of the circuit in figure 73. So in this, to determine the cutoff frequency for a series RC circuit, we know that the cutoff frequency is given by 1 over 2 pi RC. So for this figure, for figure 73, it's easily solved by just plugging in the known quantities. So 3.9 kilo ohms for R and 0.039 microfarads for the capacitance. So FR is then equal to 1.05 kilohertz, or FC, because this is the cutoff frequency, 1.05 kilohertz for the circuit in figure 73. For the circuit in figure 74, we have FC equal to 1 over 2 pi times 1 kilo ohm times 0.1 microfarad, and that will give us 1.59 kilo ohm as the cutoff frequency. What about the bandwidth for the circuit in figure 73? We know that this type of circuit is a low pass filter. Why? Because if we take the output voltage across the capacitor, then it produces an output voltage versus frequency response that is given by this, and somewhere here, which is 0.701, corresponding to that value, we have the cutoff frequency. So in this is a low pass filter. So this circuit is a low pass filter. And we know that for a low pass filter, any signal between 0 and the cutoff frequency is allowed to pass, but all signals above the cutoff frequencies are not allowed. So in this case, the bandwidth is equal simply to the cutoff frequency, which is just 1.05 kilohertz. For figure 74, if you have a resistor, if the output voltage is taken across the resistor, then this acts as a high pass filter. And for a high pass filter, we have this type of frequency response, and in this case, anything above the cutoff frequency is allowed to pass, which means that since we don't know where or when or at what frequency this signal will die down, then essentially the bandwidth is infinite. So in this case, the bandwidth we can consider as infinite. Let's now consider this set of problems. So we have three questions here. The first question is, what is the impedance of an ideal parallel resonance circuit with no resistance in either branch? The second question is, find the total impedance at resonance and the resonant frequency for the tank circuit in this figure. And how much current is drawn from the source in figure 74 at resonance, and what are the inductive current and the capacitive current at the resonant frequency. So let's begin with the first question. The impedance of an ideal parallel resonance circuit with no resistance in either branch is infinite at the resonant frequency. Okay, we've already discussed this in the lecture, and we've seen the graph of the impedance, and that graph tells us that at resonance the impedance becomes very, very large and approaches infinity. And the reason for that is that both ZR and ZC, and the result of that, and because the total impedance is zero, and because the total impedance is infinite at resonance, the total current is zero. The total current is zero because the current through the resistor, the current through the inductor and through the capacitor are both equal. So they cancel each other out, which means as well that the inductive reactance is just equal to the capacitive reactance. So for the next question, find Z at resonance and FR for the tank circuit. So in order to find the resonant frequency for the tank circuit, we use this equation. FR is equal to 1 over 2 pi square root of LC. We already know what L and C are. They are the given quantities. L equals 50 millihenry and C equals 47 picofarad. So if you plug them in the equation, we have FR to be equal to 104 kilohertz. Now that we know FR, the next step is to find Z at resonance. So in order to do that, we first need to convert this circuit into this parallel RLC circuit, where this new resistance is then RP equivalent, this new inductance is L equivalent, and the capacitance is still the original C. So still have 6.3 volts at the input. We can solve for RPEQ using the equation R times Q squared plus 1 and LEQ using the equation L times Q squared plus 1 over Q squared, where Q is the quality factor, which is equal to the inductive reactance divided by the winding resistance, and that is equal to 2 pi FRL divided by R. We know what FR is, we know what L is, and we know what R is, so we can easily solve for the quality factor, and that computation will lead us to a quality factor of 1600. It's about 1631, but the quality factor is actually not an accurate term, and usually you round it off to the nearest tens or hundreds or whatever is convenient. We know that if Q is greater than or equal to 10, then the term Q squared plus 1 over Q squared will just be approximately equal to 1. So that means LEQ will just be approximately equal to L. What about the resonant frequency? The resonant frequency, or the equivalent resonant frequency, when we have this winding resistance, is given by this expression, Q squared over Q squared plus 1. But since we know that Q squared over Q squared plus 1 is just equal to 1, then since Q is equal to 1600, then the resonant frequency, the equivalent resonant frequency is just FR. Now that we've figured those things out, so we now return back to our task of finding the total impedance at resonance. This tank circuit at resonance has an impedance which is equal to infinity, or it has an infinite impedance at resonance. Now this has a finite value. The value of that is just equal to R times Q squared plus 1. We know what R is. R is 20 ohms and Q is 1600. So if we plug all that in, we get our PEQ to be equal to 53 mega ohms. So this 53 mega ohms is in parallel with an infinite impedance. So if we compute for the total impedance, we have 1 over R PEQ plus 1 over ZLC, and take the reciprocal of that, we have this. Since this is infinite, then this term is just equal to 0, which means that the total impedance is just equal to RPEQ. And since RPEQ is equal to 53 mega ohms, the total impedance is also equal to 53 mega ohms. This is only at resonance. How much current is drawn from the source in figure 74 at resonance? So we know that since this is infinite, we know that this tank circuit doesn't draw any current at all from the source. Only this resistor draws current from the source. So we can easily solve for that current to be equal to 6.3 volts divided by Z, or RPEQ, which is 20 ohms. So 6.3 volts divided, not 20 ohms, which is 53 mega ohms. So the current is then 0.19 microamperes. Now for the last question, what are the inductive current and the capacitive current at the resonant frequency? So we've discussed that at resonance, the tank circuit has an infinite impedance. So why is it that we're being asked to solve for the current across the inductor, or through the inductor and through the capacitor? Well, that's because there's an exchange of current between the inductor and the capacitor. And even though there's an exchange in current between these two devices, none of the current is being drawn from the power source. They're really just exchanging energies, charging, the capacitor charging and discharging while the inductor energizes and de-energizes. Okay, so that's the current that we really want to solve. We know that at resonance, these two currents must be equal, because by being equal, it means that these currents cancel each other out. And because they cancel each other out, the impedance becomes infinite. Now let's solve for this current. What we're going to do is to solve the current at each branch. So we're first going to solve the current here. Okay, in order to solve for the current there, we need first to get the capacitive reactance. And once we get the capacitive reactance, we then solve for the capacitive susceptance. We know that they are just reciprocals of each other. The next step is to solve for the current in this branch. The current in that branch is given by the series combination of these RL devices. So this is nothing but R plus J omega L. And once we know the impedance across RL, then we can get the admittance across RL, which is nothing but the reciprocal of this impedance. So XC is equal to J over omega C, or omega is equal to 2 pi FR. So we're just talking at resonance here. XC, plugging in the values, gives us 32.6 kilo ohm J. In this case, BC will then give us negative 30.6 microsiemens. And of course, we have to put J there. Now let's solve for ZRL. ZRL is 20 ohms plus J times 2 pi FRL. 2 pi FRL, after plugging in the known values, gives us 32.6 kilo ohms. Okay, and once we know that, we can solve for YRL, which is just the reciprocal of ZRL, and doing the mathematics gives us 1.88 nanosiemens for the real axis and 30.7 millisiemens or microsiemens for the imaginary axis. Now we can solve for the current through the capacitor. And the current through the capacitor is given by V sub S times the magnitude of BC. Okay, the magnitude of VC is 30.6 microsiemens. So that's 6.3 volts times 30.6 microsiemens. This gives us 0.19 milliamperes. And for the current through the resistor and inductor, we have V sub S times the magnitude of YRL. The magnitude of YRL is obtained from solving the sum of squares of the components of RL along the real and imaginary axis. So that's 1.88 nanosiemens and 30.6 microsiemens squared, and you take the square root of that. Okay, and that's what we plug here. So IRL is equal to V sub S, or 6.3 volts times about 30.6 microsiemens, which is also equal to 0.19 milliamperes. So we see that these two currents are actually equal as expected, because these currents just exchange direction and the energy is just exchanged between the capacitor and the inductor. In this next example, the question is asked, what values of L and C should be used in a tank circuit to obtain a resonant frequency of 8 kHz? The bandwidth must be 800 Hz and the winding resistance of the coil is 10 ohms. So we know that it is given that the resonant frequency is 8 kilohertz. Now the bandwidth is related to the resonant frequency from this equation. So from here, we can solve for the quality factor. So 8 kilohertz divided by the bandwidth of 8 hertz gives us the quality factor of about 10. Now we know that the quality factor is also equal to 2 pi FRL over the winding resistance of the coil. Since we already know FR and the winding resistance of the coil is 10 ohms, we can solve for the inductance. So we can write the inductance as L equals 10 ohms divided by 2 pi times 800 hertz, which gives us a value of 2 millihenry. Now that we know that, okay, we also know that FR is equal to 1 over 2 pi times square root of LC. So since we already know L, we can solve for C. Rewriting that, we have the expression for C as C is equal to 1 over 4 pi squared FR squared L. And by plugging in the known values, we get the capacitance to be equal to 0.200 microfarad.